Let's move right into chapter 1. If you're following along with the 4th edition, this is just going to do some basic concepts and introductions, but if you're not, the books do tend to progress pretty similar. And so again, just the introduction and basic concepts for this. So here's the image showing the thermal plume produced by Professor Simbala as he welcomes you to the fascinating world of fluid mechanics. So I know this is pretty cheesy, but fluid mechanics is very, very interesting. Here's the objectives. We're not going to go through them since we're going to go through the entire chapter. So let's start off with what mechanics actually is. So it's the oldest physical science that deals with both stationary and moving bodies under the influence of a force. So if you have, let's see, a chair, and someone is sitting on it, right? There's a force that this person is applying on this chair. Yay, he's so happy. Okay, so he is applying a force here, and that's a stationary body. But if this same person here is pushing the chair, he is also applying a force very happily. And this is a moving body under the influence of a force, right? So this chair is stationary and this one is moving. And this is the body that we're looking at, the chair, looking at the individual chair, not the body of the person. The body of the person is the force. That is the influence of the force. So statics is the branch of mechanics. So under mechanics, that deals with the bodies at rest. So statics. And then dynamics is the branch that deals with the body in motion. And just to give you a little bit of excerpt, dynamic means the change or to change. And so that's a really good way to remember, especially if you're going to take thermodynamics, things like that. They're dynamic courses. Those deal with changing of, right? So if you have a dynamic portion of mechanics, it's going to be dealing with motion, whereas static is going to be at rest. And so then fluid mechanics is the science that deals with the behavior of fluids at rest, which is fluid statics, or motion, which is fluid dynamics, and the interaction of fluids with solids or other fluid boundaries. Okay? And then fluid mechanics is also referred to as fluid dynamics by considering fluids at rest as a special case of motion with zero velocity. Okay? And so technically, if you really want to get into it, you can say, well, if you have fluid mechanics, you can break that down. Fluid mechanics, you can break that down into statics or fluid statics and then fluid dynamics. But you will almost never see a fluid statics course, right? We wouldn't devote a whole semester to it because it's fluid. When is fluid ever not in motion? It's very rare, right? So what we do is we study fluid mechanics, which is almost all fluid dynamics. And then we just talk about fluid statics in a small special case situation because they're just compared to fluid dynamics, they're very rare. So hydrodynamics is the study of the motion of fluids that can be approximated by incompressible. So hydro, right? The liquid. Let's break that down. So we have, let's just say fluid. So we're in a fluids class. So let's say fluid and then change, right? Hydro, so fluid, and dynamics we just talked about means to change. So the study of the motion of fluids that can be approximated as incompressible. And we treat most liquids, especially water, and gases at low speed as incompressible, which means that their density stays the same. Okay, so if you have water in your hand and your palm is just open with the water in it, it has a certain amount of density there. And if you squeeze your hand and somehow you're able to keep all of the water in there, maybe it's in a balloon, or something like that, the water's not going to compress. It's incompressible, right? Whereas if you have Play-Doh, right, in your hand and you squeeze it, it will get smaller. Its density will change. Okay? So that's what we mean by incompressible. Hydraulics is a subcategory of hydrodynamics, which deals with liquid flow in pipes and open channels. So this is just the route that some of these liquid flows experience under hydrodynamics. Okay? And then gas dynamics deals with the flow of liquids that undergo significant density changes, such as the flow of gases through nozzles at high speeds. Okay? So hydrodynamics is incompressible. Oops. Sorry, guys, I'm using a pen, and it has buttons on the side, and I apparently keep pressing the buttons. Let's hope I get a lot better at that. So incompressible for hydrodynamics, and then for gas dynamics, it is significant density changes. And that can be because of compression. It can be from other types of forces. Anyway, when we talk about incompressible, it means that we're not going to have a density change. And when we talk about gas dynamics, we are going to talk about density changes. And the reason why is because most liquids are incompressible. So that's why we have it as hydrodynamics. And gases are where you are going to find that density change when we're talking about a fluid. And so that's why we call it gas dynamics. So if you have a lot of vapor coming out and it's just in the environment, well, it's going to be spread out. But if you're somehow able to capture that and squeeze it, you can absolutely compress that. Aerodynamics deals with the flow of gases, especially air, over bodies such as aircraft, rockets, automobiles at high or low speeds. Okay? And then meteorology, oceanography, and hydrology deal with naturally occurring flows. So these are non-man-made, right? Naturally occurring flows. A waterfall, right? Things like that. So what is a fluid? A substance in the liquid or gas phase. Okay? And so we have 3 phases, right? So we have a solid, a liquid, or a gas. And so a fluid, let's write that up here. So you have 3 phases, and it could be a solid, a liquid, or a gas. And for us, our fluid is in the liquid or gas phase. Okay? A solid can resist an applied shear stress by deforming. And so when we talk about deforming, we talk about the change from the starting point and an ending point, right? So if you have something that has deformed, that means it's not the same that it originally started at, okay? So you see this rubber right here. Oop, yep, not getting better, but we're working on it. So you see this rubber, it started here. It started at the bottom, right here. And then some form of force right here at the top is pushing this way, which is deforming it, right? Because it started at this as this square or this rectangle right here. It started here. And then we had a force above the top which changed it to look like this. And it was deformed rubber, right? And so this change from the starting point to the ending point is shear strain. So strain received from the deformation, right? We have the contact area, that's the A, right? We have shear stress, force over area, and then we have the force that's applied, okay? A fluid deforms continuously under the influence of a shear stress, no matter how small. So it doesn't just happen all at once. It happens over time, and it's a continuous. In solid, stress is proportional to the strain, but in fluids, stress is proportional to the strain rate, right? So if you have water, if you have a boat sailing across the water, that fluid is going to experience deforming. You can see that by way of waves. You can see the deformation of the water. If the water was perfectly still before and a boat starts going across it, it's going to deform, and you're going to see that by a wave. And that deformation is going to deform continuously. But if you have a road with a vehicle on it, well, the amount of deformation from the bicycle going over the road is going to be so small. Well, you know what? Let's not even say a road. Let's say like a dirt road. That way you can picture it in your head. If you have a dirt road and you have a bicycle traveling on this dirt road, you will also see deformation, very small tire tracks. That's what you will see. The difference between that and a dump truck driving over this dirt road is going to be extreme. And that's because in solids, like the dirt, stress is proportional to the strain. The strain that the dump truck is applying is much greater than a bicycle. So the stress that the dirt road is going to receive is going to be proportional or much greater at the dump truck than the fluid. But in the fluids, the stress is proportional to the strain rate, okay? And that is because the fluid deforms continuously. When a constant shear force is applied, a solid eventually stops deforming at some fixed strain angle, whereas a fluid will never stop deforming and approaches a constant rate of strain. Okay? And so that's because, let's say we have a concrete block, okay? And we start adding weights onto it, and we have infinite amount of weights, right? And we add them in 5-pound increments. Well, it will deform proportional to the stress that's being applied, and eventually it will stop deforming because it will break. It will eventually get to the point to where it has deformed so much that concrete block, that thing that we're looking at, has failed or has broken. We call it failing when we're testing it. So it has failed. So it's no longer going to be deformed because it's not a concrete block anymore to deform. It's not a concrete block anymore. It's now little bitty shards of concrete. So you're no longer deforming the concrete block, right? But what if you just keep applying boats to this lake, you know? Well, the fluid's just going to, or what if you have the boat that's just never going to stop going on this lake, right? It's still going to deform. And eventually it will deform, or it will continue receiving that shear force, right? At a constant shear force, so a constant rate. So the boat's going at the same amount of speed. And it will eventually just get to the point to where it's deforming at the same rate. Nothing's changing. It's not getting less. It's not getting more. It's just going to keep making these waves in the same amount, in the same rate. You know, it's just going to experience the same. That's because you're not breaking water, right? Water's not going to fail under a force because it's incompressible. So here's just a little note: deformation of a rubber block placed between two parallel plates under the influence of a shear force. The shear stress shown is that on the rubber, an equal but opposite shear force acts under the plate. Okay, a stress is just a force per a unit area. So the stress is the byproduct of the force. So you have the force, and if you calculate that on a per unit area, so like on a item, then that is the stress. Normal stress, the normal component of a force acting on a surface area per unit. And just to note here, you do have a normal to view. And that's basically how we are going to look at things. So you see this XY axis. So this is the X and this is the Y. Right here, starting at like the origin, going straight up, or some people say that it's easier to look straight down at the origin. That is normal too. I think of yourself standing on the there. You are normal too. If you are standing sideways, you are not normal too. Okay, so when we say normal too, we think of it on an XY axis. My Y looks like an X. There you go. So shear stress is the tangent component of the force acting on a surface per unit area. Okay, and then so these are obviously, you see that they're very dependent on the angle and on the, if it's XYZ axis. The pressure is the normal stress in a fluid at rest. Okay, so it's just the normal stress in a fluid at rest, right? And then zero shear stress is a fluid at rest is at a state of zero shear stress. So when we're talking about zero shear stress, it's just a fluid at rest. And this is often where we start our analyzing, because we're going to start and we're going to analyze things kind of like a beginning and end. We're going to analyze what happens in between. And so this zero shear stress is a really good place to start that. When the walls are removed or a liquid container is tilted, a shear develops as the liquid moves to reestablish a horizontal free surface. Okay? And that's because in the natural order of the world, we are trying to reach equilibrium, or we're trying to reach at rest, right? Where things are moving to the minimal amount possible, right? So it's trying to get back to equilibrium or back to rest. And you can think of this when you spin around really fast, or if you've ever felt really dizzy, and you hear that sometimes, you hear people saying, oh, my equilibrium is off, and your body's desperately trying to get back to its at rest portion, right? The normal stress and shear stress at the surface of a fluid element. For fluids at rest, the shear stress is 0, and pressure is the only normal stress. And that's because everything has a pressure, right? Water has a pressure, atmosphere has a pressure, things like that. And so we don't start pressure at 0, but it does have, each fluid or each body has its own pressure that it has. And so therefore that is its starting point. Okay. And so you see here tangent to the surface, and then normal 2. So right here you're going to be tangent. Being tangent's not sad. It's just not normal 2. And then this is the force acting on an area, right? So we've got dF here. And you can denote each force. So when we are talking about a force, we use this little subscript to denote which force we're talking about. So that's normal 2, and then here's tangent. And when I want you to think about subscripts, I want you to think about that as labeling. This is it's like his little name tag. So that's N, and this is his little name tag, which is T for tangent. And so that's so when you are calculating that you and I both know which force you are referring to in calculating. In a liquid, groups of molecules can move relative to each other, but the volume remains relatively constant because of the strong cohesive forces between the molecules. As a result, a liquid takes the shape of the container it's in, and it forms a free surface in a large container in a gravitational field. Okay, so this is just saying here that the volume remains relatively constant because of strong cohesive forces. And so you have all these little molecules here, and they have cohesive bonds, cohesive forces, right? And so that looks kind of like a ball. And then if you put it into a box, we're going to have these molecules still here. They may change shape, but they're still going to have cohesive bonds, and they're going to stay together. However, a gas expands until it encounters the walls of the container and fills up the entire space available. This is because gas molecules are widely spaced, and the cohesive forces between them are very small, unlike the liquid. A gas in an open container cannot form a free surface. So you see this free surface here, right? This is the free surface of a liquid. It's the top of the liquid, right? Of course, you can penetrate that free surface. That's fine. You can dip your finger in the liquid, right? Or put ice cubes in it or stir it around. But it's going to form a free surface, the surface of water, the surface of the lake, the surface of the ocean, right? That is a liquid body with a free surface. But a gas is not like that. If you, the dryer vent that exits your house or your apartment or things like that, that expels a gas or a vapor. And that's not just staying all together, right? That's not just a block of glass, a block of gas or vapor that's coming out. It's expanding into the environment, and it will continue to expand until it cannot expand anymore, which is the atmospheric bounds. That's the pressure that keeps our atmosphere in. So if you think here, and this is Earth, and then you have our atmosphere, which I'm going to say atmosphere. Right here, you have an atmospheric pressure. Okay? And so here, if you have, obviously this is not proportional, right, guys? But if you have a chimney and you have some smoke going, this smoke is going to go all over. It's going to fill up forever and ever and ever and ever and ever until it changes state, maybe into a liquid, or vice versa and back into it. But it's always going to stay within the atmosphere because the pressure is giving it walls. This is the wall that the gas has to stay into. The ocean doesn't have to do that. The ocean's going to stay right here, right? It's going to stay right here because it's going to form a free surface, right? It's because the bounds, the connections between these forces are so weak, it can't keep them together. So the intermolecule bonds are the strongest in solids and weakest in gas, and that's how we get form. Okay, that's how we take shape. Molecules are arranged in a pattern that is repeated throughout, and you see these are very uniform bonds, very structured. Think of this, you know what, let's take the same material, just in 3 different forms. Let's look at water, right? So H2O. H2O in this form is going to be ice. When you put ice on the counter, let's say in a room that's 30 degrees Fahrenheit, it's going to stay this. The bonds are going to stay the same. They're going to be arranged in a uniform pattern, repeated throughout, and they're going to be very strong bonds and they're not going to move. What if we raise that room's temperature to, let's say, 50 degrees, right? It's going to start melting, right? And then over time, it will continue to melt. And then these bonds are going to weaken. They're not going to look like this anymore. Now it's going to be water, right? And so those bonds are going to weaken, and we're just going to have a free surface, right? We're going to have an ice cube here. And here we're going to have a glass of water. If it's in a glass, right? If it's not, it's just going to be on the table, but it'll still have this free surface. But what happens if we raise the temperature enormously? What if it's 400 degrees Celsius, right? Or 400 degrees Fahrenheit. Here you're going to have gas or vapor, water vapor, or superheated, whatever you're looking at. This is a gas. So the bonds now have broken down so tremendously that they cannot keep the molecules together. They cannot order them, right? Molecules are far apart from each other, and molecular ordering is non-existent. There is no order to it, right? And then in the liquid phase, molecules can rotate and translate freely. They can just move around. And then in the solid, they're very uniform. They're put together, okay? So gas and vapor are often used as synonyms, and gas is the vapor phase of a substance, and it's above the critical temperature, and then vapor usually implies that the current phase is not far from the state of condensation. So when we talk about gas and vapor, they are, like it says, typically used as synonyms. But the way that you can think of gas and vapor is not very far from condensating because there is temperature, right? Anything above the boiling point, when we start to have a vapor, the bonds are now not strong enough to keep it together, but you can keep heating it. You can only heat liquid to a certain amount before it boils and becomes a vapor. But you can keep heating that vapor, and we can go up and up and up and up and up, and that's when we get into a gas. And in thermodynamics, maybe you've taken it, maybe you haven't. It's another class that I teach and I love dearly. It complements fluid mechanics and fluid dynamics very well. So in thermodynamics, lost my train of thought for a moment, you can have a PV diagram or it's a PVT diagram. And so you'll have volume on this side, and you will either have pressure or temperature on this diagram. I'm not going to go too far into it because you do go very far into it in thermodynamics, and maybe later here we'll discuss a little bit more. But for right now, we're just going to take it on a very basic level. So right here at the very top of this bell curve is this critical point. This is right here. That's the critical point, or the critical temperature. So you know what? They give this. Okay. So here is pressure. And this line right here is temperature. So this line that I just drew is temperature. So this critical point is going to be the critical temperature. Okay? And so when you have a fluid, like a water, starting out over here, and we're applying more pressure and it's heating up, this is going to be a liquid all the way on this line. You can't really see it, but that says liquid. You're going to have a liquid all the way up on this line until you get to this critical temperature, and then it's going to go to a vapor. And can you guess what that critical temperature is? Well, if we're looking at water, it's the boiling point of water, right? If we're looking at another fluid, maybe some type of oil, it's going to be the boiling point of that oil. It's going to be the point at which whatever the substance is that you're looking at changes from a liquid to a vapor. That's the critical temperature. Okay? If you exist outside of that, let's say you don't exist on this line, right? Maybe you're outside of this. Well, this critical temperature also gives you a nice halfway point where everything in this region is the liquid and everything in this region is the gas or vapor, right? And then everything under here is called a two-phase mixture, and this is both liquid and vapor. This is both under the bell curve. But outside of it, on the right side of the critical temperature, is the gas and vapor region. Okay? And so as we approach, say our point is right here, and as we approach this line right here, this vapor line, and getting into a two-phase mixture where we have some liquid here, that's when we're in a vapor. But say we're right here, say we're right here, and we start going up and up and up and up and up, and now we're over here. Now we're getting into a gas. We're leaving the vapor. We have less and less and less exposure to the liquid. Okay? Macroscopic or classical approach, it does not require a knowledge of the behavior of individual molecules and provides a direct and easy way to analyze engineering problems. That's because we're going to be looking on it on a macro scale, on a large scale, right? We don't want to know what the molecular, well, let me rephrase that. I don't need to know what the individual molecular behavior is when I'm looking at it on a macro scale. I need the big things, or the classical approach, right? But on a microscopic, a small approach or a statistical approach is based on the behavior of large groups of individual molecules, okay? So it's very important to note that we're looking at this. I'm a mechanical engineer, so I look at things primarily from a macroscopic approach because I'm looking at systems, I'm looking at devices, I'm looking at turbines and pumps and things like that. And so I need to know, I need to have the data of the molecular behavior so that I can compute my devices, but I don't need to know the behavior of those molecules. I just need some data points from it, right? But if I'm a chemical engineer, and I am studying it on a microscopic level and I need the behavior of these things, well, then I need to look at the microscopic version of it, right? I need it on that small behavior because then I'm looking at the bonds of the molecule. Then I'm looking at the phase change. When is the point that we take this new liquid and it goes from a solid to a liquid to a vapor, right? Then I am looking at it on there. But for the majority of it, when you're looking at an airplane, You're going to be looking at it from a macroscopic, the fluid flow from a macroscopic approach, not from a microscopic approach. On a microscopic scale, pressure is determined by the interaction of individual gas molecules, right? Those bonds. However, we can measure the pressure on a macroscopic scale with a pressure gauge. So we're not looking at the individual bonds between these gas molecules. We're just measuring the overall pressure. We're just getting some data points from it. So here's the application areas of fluid mechanics. I will save you some time. It's everywhere. It's inside the body, it's outside the body. Because fluid is anything, just not a solid. Gas, vapor, liquid. It's everywhere, right? So here's just a little note. Fluid dynamics is used extensively in the design of artificial hearts. This is a cool one. Maybe you haven't thought about this. Shown here at Penn State, the artificial heart. But of course, we've got some flow going there. Got natural flows and weather. We talked about, we talked about how we have things that occur naturally in the world, like the flow of waterfalls. And then you have power plants or dams, which are artificial flows, right? Boats, aircraft, spacecraft, human body, cars. It's everywhere. You've got blood in your veins. You've got some flow. Wind turbines, industrial applications, piping and plumbing systems. So a brief history of fluid mechanics, not going to go too much into it. It's very old. It's very old because you know what? We've had water for a very long time. Flowed things, Indoor plumbing, that was a great time for fluid mechanics. Perfect time to come up with something new. That's great. Osborne Reynolds' original apparatus for demonstrating the onset of turbulence in pipes begins operation by John Linhart at the University of Manchester in 1975. So we've come a long way. The Wright brothers take flight. So of course we've got the flow of air, right? We've got gas and liquids, right? Old and new wind turbine technologies. So here you see the difference. But mechanically, very, very different, right? Able to harness tons of the ability. Where are we? So this is the old version and this is the new version. What we are able to grasp with the new version is mountains, leaps and bounds above the old version. But mechanically, you look at it and it's basically the same. It's a stick. It's a stick with some blades. That's what we got. It rotates. No slip condition. Okay, so I'm just going to read this through and then we'll talk about it. So consider the flow of a fluid in a stationary pipe or over a solid surface that is non-porous, which means that fluid, whether it be gas, liquid, or a vapor, cannot penetrate it, like the wing of an aircraft, right? Or liquids within a metal pipe. So we're going to consider that. All experimental observations indicate that a fluid in motion comes to a complete stop at the surface and assume a zero velocity relative to the surface. Okay, so all of our experimental observations, all of them have indicated that a fluid that is moving through this pipe or the fluid that is moving over an aircraft comes to a complete stop at the surface and assumes a zero velocity relative to the surface. That is, a fluid in direct contact with a solid sticks to the surface, and there is no slip, considering the no slip condition, right? The fluid property responsible for the no slip condition and the development of the boundary layer is called the viscosity. So that's that bound. The key here is the development of the boundary layer, and it's called viscosity. And we get that development, that boundary layer is developed from the no slip condition. So what it was is we saw these fluids and going over a non-porous material. And we were seeing that we were having this development of that boundary layer. And then we investigated it further and saw that we had this no-slip condition. And it's where the fluid that comes into contact with a solid sticks to the surface. It doesn't slip across it, it sticks to it, right? And we assume that the zero velocity is relative to the surface, right? So there's nothing, it's just sticking. The development of a velocity profile due to the no-slip condition as the fluid flows over a blunt nose. So think of this and it doesn't really matter what this is, but let's just say it's a wing, because it kind of looks like a wing. So let's say this is a wing, and say the flow here is either, oh wait, does it say what it is here? Flow film. I mean, it can be air, or it can be a submerged wing with a flow of water. Doesn't matter. And you can see this little white amount, and it's sticking to the wing, right? So we're sticking here. Whoops, where did I go? Here I am. Okay, so we're sticking to the wing, and then we're coming off of it. But we have this little boundary. It's just forming. It's sticking to it, and it's sticking all the way around here. It's not slipping over it and sliding out the back. You know, some of it is, but not all of it. You see, we have this still here. We have it all the way around, right? And this is called, these portions right here, all around the wing, it's sticking to the wing. It's our no-slip condition. And we call this portion viscosity. That's what this is. All this that I just colored in, that's the viscosity. It's what's sticking to the impermeable item or surface that we're floating over. Okay? And so here you have a uniform approach, which is velocity. And so you see here, it's uniform. Starting, same distance, it's very uniform, right? And then relative velocities of a fluid layer, right? And then here, you see, because it's touching the surface, we've got some viscosity, boundary layer, right? And you see that it just starts sticking, and so you have less, right? Zero velocity at the surface, we have nothing, it's sticking. And then relative velocities of fluid layers. So as you increase up normal to the plate, you're going to have an increase of velocity because you're not sticking on the surface anymore up here, right? And so to a point, it's pretty quickly. We saw it right here, right? Pretty quickly, you're going to go from, let me erase some of this so you can see it. So pretty quickly, you're going to go from the surface to here. And so this, we have no velocity here. We may have a little bit velocity here. We have a little bit more velocity here. And now we've got a uniform velocity, right? And so we are not uniform for about this amount, right? Whatever that amount is that we would measure. A fluid flowing over a stationary surface comes to a complete stop at the surface because of the no-slip condition, because it's sticking to the surface. Flow separation during flow over a curved surface. So you can see the flow separating because we're going to have some sticking, right? And we're going to have some flowing up, continuing, because not all of it's going to stick. And so the difference, the point at which it separates is right here, and then you can see that separation grow in magnitude. The boundary layer, this is very important, is the flow region adjacent to the wall in which the viscous effects and thus the velocity gradients are significant. The boundary layer is all of this, right? So we've got a boundary layer around our surface. Viscous versus inviscid regions of flow. So viscous flows are flows in which the frictional effects are significant. Okay, so if you have something sticking, okay, think of your hands. You put glue on your hands. You start rubbing them together. They are literally sticking together. You start rubbing them together, you are going to have extreme amounts of friction for your hands, right? Based upon the amount of friction that your hands can have, right? You're going to have a lot of friction there. In viscid flow regions, in many flows of practical interest, there are regions, typically regions not close to the solid surface, which viscous forces are negligible and small compared to the inertia pressure forces. Okay, so you have viscous flow, that's going to be a lot of friction, a lot of frictional areas. And then when you get to the inviscid flow region, that's going to be like your hand. You have glue on your hands, right? And you're rubbing them together, but they're not touching. You're going to have no friction, right? It's not touching the surface. You're going to experience negligible, very small, things that we equate to zero for friction, right? So viscous flow, that's going to be that no slip. That's going to be what's going to, not completely, right? Because right here is where we're going to have the no slip. That's where it's going to, stick to the surface. But viscous flow, it really encapsulates not just the no slip, but really where that flow is just not where it should be because of the boundary layer, because of the no slip condition, because of the viscous. So this is the viscous flow. And then when you have separated and you're no longer experiencing the friction caused by the surface, that's when you're going to get into a normal flow, and that's the inviscid flow region. Okay? And you can see that above and below, the flow of an originally uniform fluid stream over a flat plate in the regions of the viscous flow next to the plate on both sides, and inviscid flow away from the plate. So here, this black portion, all right here, whoops, trying not to draw over that white line. This all is that plate, right? The white is our boundary that we have formed because of the no slip. It's the boundary layer. And then everything that is affected because of the friction from the plate right here is the viscous flow region. And then everything when we get into a pretty normal flow rate is the inviscid flow rate, or not affected by the plate, right? So you can even think of inviscid as just maybe not affected by the surface area. External flow is the flow of an unbounded fluid over a surface such as a plate, wire, or pipe. Okay? And then internal flow is the flow in a pipe or a duct if the fluid is bounded by a solid surface. So the flow of an unbounded fluid over a surface such as a pipe, wire, or plate. So it's just external to something. The wind over a wing is external. Okay? The gas being expelled from your dryer is an external flow. The internal flow, the flow of a pipe or duct of the fluid in a pipe or duct, is bounded by a solid surface. So, the materials or the working fluids in your car, right? The oil in your car is an internal flow. The blood in your veins is an internal flow, but the air around you is an external flow. Water flow in a pipe is an internal flow, and the airflow over a ball is an external flow. So internal and external. The flow of liquids in a duct is called open channel flow if the duct is only partially filled with the liquid and there's a free surface. So that would be if you have, let's draw this duct. I'm a very visual person, so I draw a lot, but I'm not very artistic with this pen, so it's not very good. But you get the point. So if we have a flow, which is why I drew it deformed, because we have a flow, We have a force here that's causing the water to flow. This is an open channel flow. If the duct is only partially filled with the liquid, and there's a free surface here. Okay, and here it's showing you a picture, an external flow over a tennis ball and the turbulent wake region behind. So this is really important because you can see the changes. You see this like sticking, this no slip here. And then you can see the changes are drastic in the viscous region and then not so much in the inviscid region, right? Incompressible flow, if the density of a flowing fluid remains nearly constant throughout. So remember, we talked about most liquids are incompressible because the density is going to change. You're not going to squish water. I mean, you may displace it, but you're not going to squish it, right? If you have a sponge and it's full of water and you squeeze it, you're not compressing the water. You're displacing it. You're moving it from the sponge to not in the sponge. But a compressible flow, if the density of the fluid changes during the flow, like high-speed gas flows, right? So if you have, your hands filled with gas, or if you're able to blow or something, some kind of gas into your hand, you can compress it. It can get smaller. And that's because you can manually tighten those bonds, the molecular bonds. Because in a gas, the molecular bonds of the molecules are spread out. When analyzing rockets, spacecraft, and other systems that involve high-speed gas flows, the flow speed is often expressed by a Mach number, and that's the speed of flow, so the velocity, over the speed of sound, which we denote as c. And then when we have a Mach that is equal to 1, that's just a sonic flow. If you have a Mach that is less than 1, then it's a subsonic flow. Let's see where my pen is. There it is. Subsonic flow, under. A supersonic flow is greater than 1, or a hypersonic flow is just really a lot greater than 1. So we've now made things so fast that it's not just supersonic, it's hypersonic, right? And so here we have an image of a spherical shock wave produced by a bursting balloon at Penn State, and several secondary shocks are seen in the areas surrounding the balloon. So you see here, you see the balloon and you see a shock, right? But you also see additional shocks, right? And this is the bursting. But you see many, many shocks. Right? Okay. Laminar flow. So that's a highly ordered fluid motion characterized by smooth layers of fluid. The flow of high viscosity fluids, such as oils, at low velocities is typically laminar. And so what you can think of when you think of laminar, think of it as just smooth, right? So if you have molasses, if you're pouring out molasses and it's a very low velocity, if you have molasses in your cabinet, you can pour it out. I mean, unless you need it, but you can pour it out and you will see it will be so slow, but there's a lot of friction. It's a very thick material and it will flow so smoothly. It will look uniform, right? It's almost like a paste. But a turbulent fluid, so that's on the opposite end. So we have something very, very uniform, very, very smooth. Turbulent, which is all the way at the end, is a highly disordered fluid motion that typically occurs at high velocity and is characterized by velocity fluctuations. The flow of low velocity fluids, such as air at high velocities, are typically turbulent. So on a really cold day, if you see the steam coming out of a chimney and it's like bellowing and it's kind of all over the place, That's a turbulent fluid that you can see, right? So it's just, you can even see it. It's like billows. It's all over the place. And then in the middle, you have a transitional flow. It's the flow that alternates between being laminar or turbulent. So sometimes it's like a little wavy. It's not all the way laminar and it's not all the way turbulent. And so is those three flows over a flat plate. And you'll see that flat plate used a lot here. Natural or unforced versus forced flow. It's exactly how it reads. A forced flow is a fluid is forced to flow over a surface or in a pipe by external means such as a pump or a fan. It's a manually forced flow. It's something that's not going to occur naturally. A natural flow is a fluid motion is due to the natural means by which the buoyancy effect, which manifests itself as it rises of warmer, or thus lighter fluid, or falls cooler, thus a denser fluid. You can think of like fog is a good natural flow. So it's one that students are really able to picture because we have fog because it's on colder days because it falls, right? And then as the temperature rises in the day, then it rises, it's lighter, and we lose the fog, right? And so here in this image, you can see a girl in a swimming suit. The rise of the lighter air adjacent to her body indicates that humans and warm-blooded animals are surrounded by thermal plumes of rising warm air. And again, if you haven't taken thermo, or if you have, this is like energy transfer, right? Because we have energy within us. And so we have the most amount of energy transfer because we're always transferring energy with our surroundings. So we have the most amount of it with our atmosphere right outside of us. Steady versus unsteady flow. The term steady applies to no change at a point with time. So when you think of like a car with miles per hour, that's always in reference to miles, which is the change, and then time, miles per hour, which is the time. Right here, this is obviously, if you are 0 miles an hour, then you have no change with regard to an hour, which is 1, right? 0 miles per hour means that you are going no miles per hour, which means you are having no change at a given point in time. The opposite is unsteady. So if you have 10 miles an hour, then you're going to have 10 miles of change given 1 hour, and that's an unsteady. In fluid mechanics, unsteady is the most general term that applies to any flow that is not steady. But transient is typically used for developing flows. So you can think of that as like gearing up. So when you start and stop, just like a car, if you want your flow or if you want your car to go 70 miles an hour, you're not just going to go 0 and then in the next moment you're going to be 70 miles an hour, right? You have to gear up to that. You have to go 0, 1, 2, 3, 4, and every infinite point in between until you get to 70 miles an hour. That's that transient, right? So that's a developing mile per hour. It's a developing speed point. Or if you have a flow that you are getting to, then you have a developing flow to get to there. The term uniform applies to no change with location over a specified region. I want you to think of that like an ice cube, right? So over a specified region, over the block, there's going to be no change. The term periodic refers to the kind of unsteady flow in which the flow oscillates about a steady mean. So many devices such as turbines, compressors, boilers, condensers, heat exchangers, which are all things that we operate within thermodynamics, they operate for long periods of time under the same conditions, and they're classified as steady flow devices. Okay, so I want you to think of like your refrigerator has compressors, has condensers in there, and we need that to work all the time. You need your refrigerator, you need to plug it in, And ideally, you need it to never, ever break, right? Of course, we know that parts run out. We know that, that just because because it's a man-made device, right? Our condenser and boiler are not going to last forever. But we assume those as steady flow devices because that's how they're modeled. We need them to operate under the same conditions for very long periods of time. Let's go ahead and stop here because I think we've reached about an hour, and we will pick up with lecture 2 and hopefully finish chapter 1.